Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is the fourth video of Lecture 2.1, the Basic Probability and Statistics Review. In this section, we're going to review some common analytical probability distributions. This is the third topic in our list of topics. So we're going to talk about some distributions that we can use to describe random variables. Up till now, we've been talking about variables that are naturally random, what we call natural variabilities, but we can also use distributions to describe knowledge uncertainties or values that we don't know well. So some of these distributions are useful in describing the possible range of an unknown value and the likelihood of any of those possible values. We're going to talk about uniform, triangular, normal, and log normal distributions. So starting with uniform, this is just a flat distribution that captures the fact that all values are equally likely. Okay, no preferred outcome. If you're a Bayesian, you would call this non-informative. This distribution has two parameters, A and B, or a minimum value and a maximum value. So we end up with all values being equally likely between the minimum and the maximum and not possible outside of that range. This is a symmetrical distribution. So we had said for symmetrical distributions, the mean, median, and mode are the same. So the median is just going to be the middle, where half the probability mass is above and half of it is below. So we're going to see A plus B over 2. The mean is therefore also A plus B over 2. But the mode, or most likely value, well, doesn't look like any value is most likely. So in fact, the mode is undefined for the uniform probability distribution. What does the CDF look like? Well, if we consider moving across this distribution between A and B and accumulating probability at a constant rate, that will give us a CDF that is 0 below A, a straight line between A and B that reaches 1.0 at B and then stays at that level. So we have our CDF defined on this right axis. All right, so here's the uniform distribution. A brief insert here. We had been talking about the frequency curve form of our CDF in the last segment, and note that we're back to the more familiar CDF that we saw in our college class on probability and statistics, where probability is less than or equal to on the vertical axis and our variable is on the horizontal axis. Next is the triangular distribution. This is more informative than the uniform distribution because now we have a most likely value. We have three parameters now. We have the minimum and the maximum, as we did in the uniform distribution, but we also have a mode, C, which is this most likely value. The distribution can be symmetrical, so C could be halfway between A and B and provide a symmetrical distribution, but it can also be asymmetrical. It can range as low as A and as high as B. Now, an asymmetrical distribution is very useful in describing a knowledge uncertainty because there are situations where if we're trying to describe possible values of a parameter that we don't know, and we have a best estimate, sometimes it's possible to vary further above the best estimate than we could vary below the best estimate, or vice versa. So if we can describe an asymmetrical distribution like this, we're saying that maybe C is the best estimate of that parameter, and it can go higher as a possible value than it can go lower. So we often see a triangular distribution described for a knowledge uncertainty. So we mentioned that with a symmetrical distribution, the mean, median, and mode will be the same, and that in an asymmetrical distribution, they wouldn't be. So right now we're looking at a version of the triangular distribution that has a positive skew, meaning the upper tail is longer. And in this case, the mean is dragged further above the most likely value than the median is. So in this case, we'll have the mean up here somewhere, the median back here where half the area is below and half is above, and then of course the mode is our parameter C. If we think about what the CDF looks like, again, it's going to be 0 below the minimum value, and then as we move between A and C, we'll accumulate probability at an increasing rate and then switch to accumulating at a decreasing rate above B. So our CDF will look something like this on the going from 0 to 1 on this right axis. Next, we have the normal distribution. We've seen that a lot already in this lecture. The normal distribution is the most common distribution found in nature. We see it existing all over the natural world, from the heights of all 10-year-olds to the number of leaves on all branches of a tree. The normal distribution pops up all the time, and it is also very useful in probabilistic computation. It has a defined shape and equation. Here's the equation for the PDF of the normal distribution. Earlier we saw the CDF of the normal distribution as an example. It has two parameters, the mean, Greek letter mu, and the standard deviation, sigma, or also said as the variance, sigma squared. It's a symmetrical distribution, and so the mean and median and mode are all the same here in the middle. The fact that it's symmetrical means it has a skew coefficient of 0. The normal distribution is a scalable distribution which always has the same shape but can be standardized to a mean of 0 and a standard deviation of 1. The standard normal distribution is very useful for computation because the equation is so difficult to work with. Most, or if not all, probability and statistics textbook have a tabulation of the standard normal distribution within the inside cover. So if you remember from your college class on probability and statistics, you worked with the normal distribution by scaling to the standard normal, doing computation, and then scaling back to the normal distribution. So that looked like this, where if we had a normal distribution at some location on the parameter value and some width, we would scale it down to the standard normal distribution by subtracting the mean to shift it and then dividing by the standard deviation to change its width, and we'd get this parameter z, which refers to the standard normal distribution. And we would do our probability computations, and then we would shift back to the original normal distribution by multiplying z by the actual standard deviation and then adding back on the mean to shift it. Okay, the last question on our slide is, what does the CDF look like? And we've actually seen the CDF of the normal distribution several times already, but it's just a positive accumulating at a faster rate below the mean and then at a slower rate above. So here's that nice smooth CDF that we've seen so many times in this lecture already. Some more useful points about the normal distribution is here's one with a mean of mu and a standard deviation of sigma. And it turns out that 68% of the probability within a normal distribution is within one standard deviation at either side of the mean. So 2/3 of the probability mass is within one standard deviation of the mean. If we go 2 standard deviations from the mean in either direction, we span 95% of the probability. And this is used often if we're doing sensitivity analysis to estimate a probability distribution for a knowledge uncertainty, for a parameter that we don't quite know. So we might do sensitivity analysis to come up with a possible minimum and maximum value of that parameter, and then decide that the range we've been able to determine spans 95% of the possible range. And so we'll take the distance between the minimum and the maximum, and we'll divide by 4 to represent these 4 standard deviations. So the range divided by 4 is an estimate of standard deviation to use on the distribution of knowledge uncertainty for that parameter. So you'll see this later in the week. Okay, finally, we have the log normal distribution. And this is a distribution for which the log of our variable x has a normal distribution. It might be natural log, it might be base 10 log, it could be log of any other base. Most often in other fields, you'll see natural log, but in hydrology, we do often use base 10 log. Has a defined shape and equation. Here's the equation down here, and this version is using the natural log. The parameters are a mean and a standard deviation or variance, but it's the mean of the log of x and the variance of the log of x, or standard deviation of the log of x. A quick add-in here, note that the mean of the logs is not equal to the log of the mean when you're using data to estimate parameters. So that's an important point to note when you're doing the workshop this afternoon. It has a defined skew. We can see from the PDF that this is not symmetrical. It has a positive skew with a long upper tail, but it's not always the same skew. It has a skew that is defined by the ratio of the standard deviation to the mean. So the larger the standard deviation, the more this upper tail will extend. And I guess it's going to be this way, given that I'm looking at you from in front. A useful thing about the log normal distribution, and an important point, is that it can't be less than 0, right? The log of 0 is undefined, and there is no log of values below 0. So this distribution must always be positive, and that makes it useful to use for variables that cannot be negative. Okay, what does the CDF look like? Let me add that in. Here's the CDF of the log normal distribution of this particular ratio. There's another distribution that we're going to use this week, which is the Pearson type 3 distribution and the log Pearson type 3 distribution. And I'm not showing them here, but we'll get to them a little bit later. Here's a slide that we've seen before, parameters and statistics. A parameter is a descriptive measure of a population, and we've just seen the parameters of each of those common analytical distributions. And a statistic is the same descriptive measure of a sample. A sample statistic is often used to estimate a population parameter. That's what we're going to be doing in the next section when we fit probability distributions to our data. Okay, if you have questions about these probability distributions, go to Discourse and type them in. I will try to be there to see and answer the questions. Our next segment is going to be on fitting probability distributions to data. That is it for this segment, and thank you.